So there are two laws of Michael Faraday that pertain to electrolysis. The first law is that the amount of chemical change, or you can say product produced, at an electrode, that be the cathode or the anode, with a constant current is proportional to the amount of electricity used. And what that really means in layman's terms is that the longer you leave the circuit running, the more product you're going to have, because it allows more to be produced since the reaction is driven by the electricity provided by the circuit. Now, in mathematical terms, that would be equal to moles of electrons is equal to Q over F, where the Ne refers to the moles of electrons transferred, so that would be from the anode to the cathode. The F in the formula represents the Faraday's constant, and that is a number of 9.65 times 10 to the 4, and that's charge per moles of electrons. And the Q represents the charge in coulombs, where the Q is the charge of the electron, and that's equal to the current measured in amps multiplied with the time, which must be in seconds, and please keep that in mind. The second law states that the amounts of products produced by the same quantity of electricity are proportional to their equivalent weights. That is a mouthful, but in this video and in this course, we primarily focus on just the first law and how to use the formula. So in our first example, it states that what is the mass of copper deposited at the cathode? Remember that mass builds up at the cathode of a copper electrorefining cell operated at 12 amps for 40 minutes. Now remember that we have to convert the minutes to seconds. And so in order to do that, we're going to multiply by 60. And when we plug that into our calculators, we should get a value of about 240 seconds. Now, like everything else, there are steps that can help us go through the process a lot easier. The first thing we're going to do is write a half reaction of the metal in the question, whatever that metal may be. Then we're going to find the moles of electrons, and you can do that two ways. You can do that through stoichiometry if you're given a mass, or if you're given enough information to find the Q, then you can use the first law formula of Faraday, which is Q over Faraday constant. Then the third part is always going to be to solve for the required or mass produced with the moles of electron you got from step 2. Either way, you're always going to do stoichiometry at least once. So if you go through the entire problem and you realize you haven't done stoichiometry, that means that there's something wrong. So, keeping those steps in mind, the first thing we're going to do is write the half reaction for the metal in question, which would be copper. So the mass of copper is going to be produced. We look in our data booklet. Copper 2 plus, as it gains 2 electrons, will become copper solid, and that's the half reaction at the cathode. Now, one thing I do want to keep in mind is that you could write this as a reduction or oxidation half reaction. Sometimes you'll have the mass at the anode disappearing, and so that would be an oxidation reaction. But remember that the equation would just be written backwards, and so the proportions would be the same, so it doesn't really matter. The second step is that we're going to get the moles of electrons. Now, in this question, we have the amps and we have the time. So we're actually able to get the charge, or the Q. And if we can get the charge, or the Q, then we can easily find the moles of electrons. So here, I'm plugging in 12 amps multiplied by 240 seconds. And when we plug that into our calculator, we get a value of, just plugging it in here, about 2,880 seconds. Or coulombs, I should say, not seconds, coulombs. Now we plug in the formula. The charge is 2,880 coulombs over the Faraday's constant, which is 9.65 times 10 to the 4 coulombs per mole of electrons. And once again, when you plug that into your calculator, and I've made sure to cancel out the units over here. When you plug that into your calculator, you should get a value of about 0.298 moles of electrons. And remember, label your work, because when you do a lot of calculations or multi-step questions like this, it could get complicated. Now with the moles of electrons, I'm going to solve for the mass of copper produced. And I'm going to do that using stoichiometry of the half reaction that we first wrote. So 0.29 moles of electrons. When you look back at the half reaction in step 1, there's a 2-to-1 ratio between copper and electrons. It actually should be not copper 2+, but copper solid, because that's what we're trying to find. But either way, the ratio is still the same. So 1 mole of copper solid per 2 moles of electrons. When we plug this into our calculator, we should get about 0.149 mole of copper solid produced, not copper 2+. Now we're going to multiply this by the molar mass, because we do want the grams or the mass. And when I plug that into our calculator, we get about 9.48 grams of copper solid. And that's how much is going to be produced at the cathode. Okay, remember that the mass builds up at the cathode. All right, let's look at a second example. Here it says silver is deposited on objects in a silver electroplating cell. If 0.175 grams of silver is to be deposited from a silver cyanide solution, so remember that's aqueous, in a time of 10 minutes, predict the current required. Now what I'm doing over here is that I'm converting the time right away to seconds, and I do that by multiplying by 60. Now here we're given a mass. So, according to the steps, if we're given a mass, after I've written the half reaction, which I've done over here, Ag plus 1 electron as it's getting reduced produces silver solid. If we're given a mass, we're going to use stoichiometry to get the moles of electrons. And another way you can know this is that I actually don't have enough information to find the moles of electrons using the Faraday's law formula. So if I had current and time, then surely I could. But in this case, I don't. I only have mass and I only have time, and I would need a current. So, since we don't have enough information to find the charge, we're going to use stoichiometry. And what I'm going to do with regards to the stoichiometry is I'm going to convert this to moles by dividing the amount of grams by the molar mass of silver. And when you plug that in, you should get about 1.62 times 10 to the negative 3 moles of Ag. Now with those moles of Ag, I'm going to use stoichiometry to get the moles of electrons. Remember, that's always going to be step 2. So 1.62 times 10 to the negative 3 moles of silver multiplied by 1 electron over 1 silver solid. That refers back to the reaction up in number 1. And then we're left with about 1.62 times 10 to the negative 3 moles of electrons. Now remember that in this question, what we want to do is we want to solve for current. So the moles of electrons that I've just found, that could be the Ne in our formula. So what I'm going to do here is I can expand this to I times T over Faraday's constant. And then I know that I'm solving for I. I'm going to cross multiply Faraday's constant, which would leave I multiplied by the time in seconds on the right-hand side. And then I'm going to divide both sides by T to isolate for the current, or I. When I isolate for the current, I have moles of electrons multiplied by Faraday's constant over time. I plug in my values, and that should actually be 1.62, not 1.26. 1.62 times 10 to the negative 3 moles of electrons multiplied by the time in seconds, which we converted before, which is 600 seconds. Actually, that'll be divided by, we're going to plug in Faraday's constant first, so that's 9.65 times 10 to the 4 charges per mole. And then we're dividing by 600 seconds. So not multiplying, but dividing by 600 seconds. And when you plug this in your calculator, you should be getting about 0.261 amps. And remember, when you're using numbers with scientific notation, please put the brackets. Most calculators get confused. You could write it in amps or in charges per second. A charge per second is an amp or an ampere. So that is the unit of current. So now I want you to pause the video, write this problem down in your notebook, and try it out yourself using the steps or the guidelines provided. When you're ready, unpause the video and see how we approach the solution. The last part we're going to do here is just something called regular cell stoichiometry. So that's, really using redox reactions that are happening in the entirety of an electrochemical cell, but there's no mention of current or time. And so the steps that we're going to be using to solve these are going to be as follows. And so to solve these kind of questions, the process is relatively straightforward. You're going to write a balanced redox reaction, and this is going to be using the half reaction method, okay? And it's going to come from from spontaneity, really, that the steps that you apply to write the redox reaction of a spontaneous reaction is going to be the same steps you would take here. Once you got your redox reaction, you're just going to convert substances to moles and solve for the required or whatever the question is asking for using stoichiometry. And then if you need to convert anything to grams or to kilograms, that can be done as kind of a partial last step. But really, I would say that your attention should be on making sure that you get that balanced redox reaction right. So an example of this would read, during the electrolysis of molten aluminum chloride. So remember that key term molten means that there is no water, okay? So when you list your reaction entities, do not list water. Aluminum chloride in an electrolytic cell, 5.4 grams of aluminum is produced at the cathode. Predict the mass of chlorine produced at the anode. Now, although this is an electrolytic cell and the reaction is not spontaneous, what you're going to do is still write two half reactions, one representing the anode and the cathode. So the first thing we're going to do is make sure we get that balanced redox reaction, where we're going to label everything that is present inside this cell, which, if the compound is aluminum chloride, what we really have is aluminum 3+, and then chloride Cl minus. And there is no water since it's not a solution. It is liquefied, but it's not a solution. So we will just list these two entities. And then when we look in our data booklet, we can see that aluminum 3 plus, or the aluminum ion, is an oxidizing agent, and that chlorine is a reducing agent. And since there is no other oxidizing and reducing agents, each of these are going to be the strongest of each. So aluminum 3 plus is going to be the strongest oxidizing agent, and chloride is going to be the strongest reducing agent, which further means that this is going to be the reaction at the cathode, and this is going to be the reaction at the anode. And what we're going to do is set up half reactions at both the cathode and the anode. So here I have the reduction of aluminum at the cathode. Al3 plus 3 electrons gives you Al solid. And then I have the oxidation of the chloride ion at the anode, and that would produce chlorine gas at the cathode. Now I want to combine these two reactions, and in order to do that, I have to find the lowest common multiple between the 2 and the 3 here so that we can remove the electrons from the final reaction, because the processes of oxidation and reduction should balance the electrons that are lost and gained. So the lowest common multiple between 2 and 3 is 6. So we're going to multiply this side by 2 to get these pair of electrons equal to 6. And then this side by 3. And remember, just like in Hess's law, you can't just multiply the electrons, but everything gets multiplied by the coefficients in each of the half reactions. That would leave us with these following balanced half reactions. And now once I got balanced half reactions, I'm going to combine them into one large redox reaction, which is going to be as follows. And what I do when I'm doing this is I add up all the reactants of one reaction on one side and all the products on the other side, between the two reactions, I should say. So that'll give me 2Al solid plus 3 Cl2 gas plus 6 electrons. We can remove any like terms, which would be the electrons here. And finally, this reaction over here is largely what we are working with here. So that's step 1 already done. So the next thing we're going to do is convert moles and do the stoichiometry with those moles. So we have 5.4 grams of aluminum given in this problem. So we divide by the molar mass, and that gives us 0.20014825796 moles of aluminum. And so with this amount over here, we're going to do the stoichiometry in order to find what the question wants, which is the mass of chlorine produced at the anode. So we're going to go 0.200148. Remember, we don't round until the very end. As inconvenient as that is, we have to be consistent. And we're going to multiply it by the mole ratio between chlorine and aluminum, which according to this redox reaction is going to be 3 chlorines for every 2 aluminums. And that would have the aluminums cancel out over here. And when you plug that into your calculator and you do the multiplication, you end up getting about 0.300222 moles of chlorine gas. And then finally, since it wants the mass of chlorine at the anode, that's always going to be in grams. So we're just going to convert this amount by multiplying it by the molar mass. We're going to go grams of chlorine is going to be equal to your 0.300222 mole multiplied by the grams per mole of chlorine, that's Cl2. So that'd be 70.9. Remember, 34.45 on the periodic table refers to just one chlorine, not two. We cross out these like terms, and then what you should be left with if you're using 3 significant digits is 21.3 grams. I hope this has helped. What you want to do now is the textbook questions assigned to you and the worksheets. And you can find lots of worksheets online. But I would prefer you go to the ones posted in the Google Classroom first.